In segment 1.5, we're going to move from talking about cryptography and we're going to move on to cryptocurrencies. Now I know that many of you showed up here for the cryptocurrency stuff and trust me, there will be a lot more cryptocurrency material in future lectures. Unfortunately, we needed to eat some of our cryptographic vegetables in order to have the background to talk about cryptocurrencies. And now you'll see when I start talking about cryptocurrencies how these pieces fit together and why the cryptographic operations like hash functions and digital signatures are actually useful. All right, so in this section I want to talk about some simplified cryptocurrencies that give us ideas about how systems like Bitcoin work. Of course, it's going to require about 10 more lectures in order to really spill out all of the implications of how Bitcoin works and what that means. But let me talk about some very simple cryptocurrencies to get the discussion started. And first, let's talk about Goofy Coin. Goofy Coin is about the simplest cryptocurrency we can imagine. And it works kind of like this. There are just a couple rules of Goofy Coin. The first rule is that Goofy can create new coins. Goofy can make a new coin whenever he wants, and when he makes a new coin, it belongs to him. So when Goofy makes a coin, it's represented by a data structure like this. Here you have the create coin operation, and there's a unique coin ID that Goofy generated, and then there's a digital signature that was put on it by Goofy, which anyone can verify. So anyone being given this can verify that the signature is valid and that it's a signature of this statement. And new coins belong to Goofy by definition because those are the rules that Goofy made. So that's the first rule, Goofy can create new coins. The second rule of Goofy Coin is that whoever owns a coin can pass it on to someone else. They can spend it. So for example, here we have the coin that I showed you before that Goofy created. And now we're going to take a hash pointer to that coin and then we're going to create a statement. Goofy's going to make a statement that says, pay this to Alice. Alice is being named by a public key here. Pay to public key Alice the coin that's represented by this hash pointer. And this is also signed by Goofy. Now, Goofy is the one who owned that coin, and so Goofy has to sign any transaction that spends the coin. And once this has happened, now Alice owns the coin. Alice owns the coin, and Alice can prove that she owns the coin because she can present this data structure here, which is validly signed by Goofy and points to a coin that was validly owned by Goofy. And so the correctness of this coin is self-evident in the system. Now Alice can move on, and she can spend the coin as well. So here we have the coin we had before. This is down here at the bottom. We have the creation of the coin signed by Goofy. Now Goofy paid the coin to Alice via this hash pointer, and he signed that. Now Alice is the owner of the coin. Now she can create a statement like this that says, pay this coin to Bob's public key, and here's a hash pointer to the coin. And now Alice signs that. So because Alice was the valid owner of the coin, which we could verify by walking this chain, now we know that this is valid and the coin belongs to Bob. So Bob is now the owner of this coin. So those are all the rules of Goofy Coin. Goofy can create new coins by simply signing a statement that he's making a new coin with a unique coin ID. And then whoever owns a coin can pass it on to someone else by signing a statement saying, pass on this coin to person X. And you can verify the validity of a coin by simply following the chain and verifying all of the signatures along the way. That's Goofy Coin. All right. Now, there's a problem, though. There's a big security problem with Goofy Coin, and we can see it in this structure here. So look at this coin here. This is the coin that Goofy made and then paid to Alice. Alice was the owner of that coin, and there's a problem. Alice paid this coin on to Bob, but now Alice makes another data structure like this, which pays to Chuck the very same coin. And this is signed by Alice. Now, if Chuck doesn't know about this thing up in the upper left, this data structure, let's say Alice just gave that to Bob and didn't tell Chuck. Now, Chuck will look at this and he'll think that this is perfectly valid, and now he's the owner of the coin. Chuck has a valid-looking claim to be the owner of this coin, and Bob has an equally valid-looking claim to be an owner of this coin, and that's a problem because coins are not supposed to work that way. This is called a double spending attack. It's called double spending because Alice is spending the same coin twice. And double spending attacks are one of the key problems that a cryptocurrency has to solve. Goofy Coin does not solve the double spending attack, and therefore Goofy Coin is not secure. So although Goofy Coin is simple and we understand its rules, it won't cut it as a cryptocurrency because it allows double spending. So in order to build a cryptocurrency that is going to be workable, we need to have some solution to the double spending problem. And indeed, the double spending problem is the main design challenge that we face in designing a cryptocurrency. So we need to somehow improve on Goofy Coin, and we'll do that by designing another coin, which I'll call Scrooge Coin. Scrooge Coin is going to be rather like Goofy Coin, except it will solve the double spending problem in a particular way. And this coin was created by Scrooge. Okay, so this is a little bit more complicated in terms of data structures, but here's one of the key ideas, that Scrooge is going to publish a history of all the transactions that have happened. This will be a blockchain, that data structure we talked about before, and it will be digitally signed by Scrooge. So anyone can, and it looks like this, of course. It's a series of blocks, data blocks. Each block will have one transaction in it. This block has the transaction with transaction ID number 73. And it has the contents of this transaction, and then there's a hash pointer to the previous block in the history. Okay, and then Scrooge will take the hash pointer, which represents this entire structure, and he'll digitally sign it and publish it. Now anybody can verify that Scrooge really did sign this hash pointer, and then they can follow this chain all the way back and see what is the entire history of all the transactions in the history of Scrooge Coin as endorsed by Scrooge. Okay. Now I said here that we put one transaction in each block. We do that for simplicity of explanation, but in practice, as an optimization, we'd really put multiple transactions into the same block, as Bitcoin does. So you can bear in mind as I talk about Scrooge Coin that that's the way we'd really do it in practice. So Scrooge publishes this history. What does the history do? Well, the thing the history does for us is it allows us to detect double spending. Because assume Alice owns a coin, and she's going to pay that coin on to Bob. And she's then later going to try to pay that coin on to Charlie. Charlie's going to notice that something is wrong, because Charlie will be able to look into the history and see that Alice already paid that coin to Bob. In fact, everyone will be able to see that Alice already paid that coin to Bob. So if she tries to pay that coin to Chuck, then everyone can see that that's a double spend, and they'll be able to reject it. Scrooge will reject it, and everyone else will reject it and know that they really shouldn't trust Alice. All right. So in Scrooge Coin, there are two kinds of transactions. The first kind is a create coins transaction, and what it does is create new coins. That's like the operation Goofy could do in Goofy Coin that makes a new coin. But here, we're going to allow multiple coins to be created in one transaction. So here's what a create coins transaction looks like. It has transaction ID number 73, let's say in this case. Its transaction type is create coins, and then down here there's a list of which coins are created. Each coin is going to have a serial number within this transaction, 0, 1, 2, etc. Each coin has a value. It's worth a certain number of Scrooge coins. And each coin has a recipient, which is going to be a public key who gets that coin as it's created. So this transaction type creates a bunch of new coins and assigns them to people as initial owners. Now we're going to have a concept in Scrooge Coin of a coin ID. That refers to a particular coin. So this particular coin here is coin ID 73(0) because it was created in transaction 73, and it was number 0 within that transaction. Similarly, we have 73(1), 73(2), and so on. So every coin in Scrooge Coin has a coin ID that we can use to refer to it. A create coins transaction is always valid. Why is it valid? Well, because Scrooge said so, and they call it Scrooge Coin for a reason. If Scrooge puts this into the history which he signs, then it's valid by definition. We don't need to worry about whether Scrooge is entitled to create coins, just like we didn't need to worry in Goofy Coin about whether Goofy is entitled to create coins. The rules of the system, which were created by Scrooge, simply say that if Scrooge wants to make coins, then that's valid. So anything he puts into the history is valid. The second kind of transaction we're going to talk about is a pay coins transaction. And this is a transaction that consumes some coins and destroys them and creates new coins of the same total value, but which might belong to different people. So over here on the left, we have an example of what a pay coins transaction looks like. This is transaction ID number 73, let's say. Its type is pay coins. We have here a list of the coins that this one consumes. All of these coins are being consumed and destroyed by this pay coins transaction. So we're going to add up the value of all of those coins, and then we're going to create a bunch of new coins, down here 0, 1, and 2, etc., just like before in the create coins transaction. Each one has a value. Each one will belong to a certain recipient. And those new coins had better add up to the same total value as the coins that we consumed. And then at the bottom, we have a set of digital signatures. This transaction has to be signed by everyone who's paying in a coin. So if you're the owner of one of the coins that's going to be consumed in this transaction, then you need to digitally sign the transaction to say that you're really okay with spending this coin. The rules of Scrooge coins say that a pay coins transaction is valid if 4 things are true. First, if the consumed coins are valid, that is, they really were created in previous transactions. Second, that the consumed coins were not already consumed in some previous transaction. That is, that this is not a double spend. Third, that the total value of the coins that come out of this transaction is equal to the total value of the coins that went in. And finally, that the transaction is validly signed by the owners of all of the consumed coins. If all of those things are true, then this pay coins transaction is valid. Scrooge will accept it. He'll write it into the history, into the blockchain, and everyone will see that this transaction has happened. One thing to note about this scheme is that coins are immutable. Coins are never changed, they're never subdivided, they're never combined. All they are is created once in one transaction and then later consumed in some other transaction. But you can get the same effect as being able to subdivide or pay on or combine coins by using transactions. For example, if you want to subdivide a coin, you can just create a new transaction that consumes that one coin and then produces 2 new coins of the same total value. And if you want, you can give those 2 new coins back to yourself. That's a way that you can subdivide a coin that you own. Similarly, you can combine coins or you can pay on a coin, in effect, by just creating a chain of transactions, each of which pass that value on in the form of a new coin to someone else. So although coins are immutable in this system, it has all of the flexibility of a system that didn't have immutable coins. Okay, now we come to the core problem with Scrooge coin. Scrooge coin will work. People can see which coins are valid. It prevents double spending because everyone can look into the blockchain and see that all of the transactions are valid and that every coin is consumed only once. But the problem is Scrooge. Scrooge thinks this is fine, right? Scrooge says, don't worry, I'm honest. But the fact is, if Scrooge starts misbehaving, then we're going to have a problem. Or if Scrooge just gets bored of the whole Scrooge coin scheme and stops doing the things that he's supposed to do, then the system won't operate anymore. And so the problem we have here is centralization. That although Scrooge is happy with this system, we as users of it might not be. So the central technical challenge that we need to solve in order to improve on Scrooge coin is, can we de-Scroogify the system? That is, can we get rid of that centralized Scrooge figure? Can we have a cryptocurrency that operates like Scrooge coin in many ways, but doesn't have any central trusted authority? In order to do that, we're going to need to figure out how to provide the services that Scrooge provides, but do it in a decentralized way, in a way in which no particular party is particularly trusted. That means we're going to need to figure out how everyone can agree upon a single published blockchain that is the agreed upon history of which transactions have happened. We need to figure out how people can agree which transactions are valid and which transactions have actually occurred. And we need to figure out how we can assign IDs to things in a decentralized way. If we can solve all of those problems, then we can build a currency that is very much like Bitcoin, which is like Scrooge coin, but without a centralized party. But in order to do that, it's going to take a few more lectures, and we hope you'll stick around and watch them. Thanks.